JAMB 2026 candidates, you all are welcome. Based on popular demand and based on the way JAMB normally repeats this question every year, questions from equilibrium. Because of the high votes from this question from JAMB UTME candidate 2026, I have decided to explain this question because a lot of students have been asking me, suggesting I explain this to them in the simplest way that they can understand, because that's what I do for a living. That's what I do. I've been doing this for some donkey years now, so I know how to do that better. And me myself, I know they stress students. I always tell you, you don't need textbooks. You don't need to be opening your textbooks 300 pages, 500 and something pages to prepare for JAMB UTME. Only watching my videos, making notes as you are watching my videos and revising your past question, it's enough for you to score 300 in your JAMB UTME. Now me they assure you this thing while I tell you so. I swear to God. Now me they assure you this thing so. This question you are seeing on the screen right now is very, very easy. Very easy, I swear. Very easy. When I settle down and explain this question for you now, you are going to understand that this question is not what you had thought that it was. Okay? It's not what you had thought that it was. Okay? So the question is not what you have been thinking. This question is easier than what you have been thinking. Or this reaction that looks like is confusing you. You are going to be liberated from that shame today. That number where they put for your head, where they say book no go enter your head, where your village people carry put for your head, where book no dey enter. Today I am going to clean it here. Let's look at the question. JAMB must repeat question 3. The question reads, in the equation above, that's this equation here now, this chemical equation here, the effect of increased pressure on the equilibrium position is that A, the equilibrium is shifted to the left, B, equilibrium is shifted to the right, C, there is no effect, D, more hydrogen gas is produced. JAMB 2026 candidates, what's your answer? Let's find out. First of all, let me thank the Joint Admission and Matriculation Board, JAMB, for always repeating these questions, for always helping students by repeating questions, because they know how hard it can be to take an exam, especially an exam that you are only permitted to take once in a year. You only see the exam once in a year. When you take the exam, anything just happen like this not after 1 year. So JAMB is doing, they are really doing a lot by repeating questions for these our candidates. So I also thank those that also help students by answering these questions in the comment section, because there are people that like they are dedicated in this thing. Like they are so compassionate, they are determined, they want others to learn, they are just disseminating this knowledge. They will just be there. You see person will take comment section, they will drop 200 and something words just explaining one question like this. Oh, I really appreciate you guys. I really appreciate you guys. I love what you guys are doing. Keep it up. One day I am going to see you guys through. I am going to see I see what you want to do. One day I will by myself. I will show love. I will show love because I like teaching. That's what I love. I love teaching. That's what I do. That's what I do. I love teaching, and I've been doing this for donkey years, man. I've trained a lot of students in the university. Both the ones that have graduated, they look up to me. They see me as their mentor. Both the active and the passive mentoring, both the direct and the indirect mentorship. All of them, mentorship na mentorship. They are all tied to me one way or the other. They are learning from me through experiences, to different things, through my book. If you are reading my book 72 hours to JAMB UTME, you are applying the unorthodox trade-offs in that book, following through my story and trying to avoid everything that I fell into. If you are reading that book, that's an indirect mentorship. That's a passive way of disseminating my knowledge to you. So if you don't have that book, ensure you get the book by sending me a DM, or you search the book on Google, 72 hours to JAMB UTME by Nkwado Augustine. So back to the question. It says in the chemical equation above, what is the effect of pressure on the equilibrium position of the system? This reaction that we have here. What is pressure going to do here? So when you don't understand equilibrium, like this, you don't enter one chance. Imagine you have entered this kind of one chance inside examination, or you look your left like this. You don't fit talk to person where they there. You look your right, you can't speak to that person. What are you going to do in such situation? Because speaking to them might even put you at risk in the examination hall. You can be caught and disqualified for the exam, and you have to wait again for another 1 year. So why not fortify yourself by taking my videos, by taking my lectures, by reading my books 72 hours to JAMB UTME, by making notes while you are taking my lectures, by studying your past question, by revising those notes that you made during my lecture when it's 3 weeks to your JAMB UTME. Why not follow my steps? The steps I use in conquering. Why not look at how to answer multiple choice questions, like questions having option A, B, C, D, E, and so on and so forth. How to answer it. When you are blank, what do you do? I expressed a lot in that book. So if you don't have that book, you are in error. So ensure to get the book 72 hours to JAMB UTME. So when you look at this reaction, on the left hand side of the reaction, the first substance we have there, or the first compound, is copper oxide. Then we also have hydrogen gas here. So on the right hand side of the reaction, we have copper metal and steam. Okay, this is steam. It's a gaseous form of water, which is steam. So they are asking us that increased pressure, what is it going to cause? in this system? Let's find out. There is one scientist called Chatelier. We are going to learn more about that chemist. His name is Chatelier. I think he's a French, I don't know, but his name sounds more like a French name. But what I mean is that he should have a French pedigree. Okay, he should have a French pedigree in one way or the other. So let's look at what we have here. Chemical equilibrium. Take note of the color coding. You can see how attractive my lecture and presentation material is. I know you love what you're saying. So why won't you learn? Why not go enter your head? I'm ready for you guys. JAMB UTME candidate 2026. We are ready to score 300 plus and above. None of my students is going to score 270 below. No, from 270 and above. That's our target. Let's go. So chemical equilibrium. Chemical equilibrium. In chemical equilibrium, the equilibrium you have there means balance. That is the meaning of equilibrium. Balance. And chemical equilibrium is the state in a reversible reaction. It only operates in a reversible reaction, where the rate of the forward reaction, that's the reaction on the right hand side, equals the rate of the what? The backward reaction. So the concentration of the reactant and the products remains constant. Hope you are making notes. Hope you are with your pen and your paper. No go the lose guard. No go lose guard free mark. Take your paper and your pen. Start making your notes now. So the concentration of the reactants and the products remains what? Constant. The forward reaction and the backward reaction, that's the rate of the two reactions. The forward reaction equals the backward reaction. That's the reaction you have on the left hand side equals the reaction you have on the right hand side. The concentration of reactants on the left hand side, that's where you have the reactants, and the concentration of the products on the right hand side of the reaction, they both remain constant. The left hand side of the reaction, you can also call it reactants. The right hand side of the reaction can also be called the product. So that's that for that. So let's look at an example. An example here is nitrogen gas. This one is 1 mole of nitrogen gas plus 3 moles of hydrogen gas react reversibly to give you 2 moles of what? Ammonia gas. And this ammonia can also dissociate to give us nitrogen gas and 3 moles of hydrogen gas. Can you see? This system is at equilibrium. So the concentration of the reactants here and the products are constant. So if you leave this reaction like this, provided the catalyst is there, everything that favors this reaction is there, or the determinant of reaction is there, this thing is going to continue to react reversibly till eternity because the system is at equilibrium. Characteristics of chemical equilibrium. What is the first characteristic? When you say characteristic of chemical equilibrium, you are trying to say, how do we know it? By their fruit, we shall know them. You know that saying. So what is the fruit of the chemical equilibrium? What are those fruits that when you see, you will know that this system is in a chemical equilibrium or this is a chemical equilibrium? The first one here is occurs only in a closed system. That's the first one. Only in an enclosed system. So in a chemical reaction that is occurring in the environment, the atmosphere, that is not a chemical equilibrium. You can't have a chemical equilibrium in such a system. It must be an enclosed system. The second one we have here, second characteristic or second fruit we have here is forward rate equals backward rate, like we explained. That's the characteristic, another characteristic of the chemical equilibrium. Then the third we have here is concentrations becomes constant but not equal. The concentrations are constant, that they are there for the reaction to occur. As the reaction takes start, now so the concentration they there, but they are not equal. The rate of the chemical reaction is equal. Left hand side and right hand side are both equal. That's for the rates. But the concentration of the reactants, that's the compounds on the left hand side of the reaction, and the products, that's the compound on the right hand side of the reaction, are not equal, but they are constant, but are not equal. When you say something is constant, it means that the thing is there, always present, but they are not equal. I want you to get that because JAMB always sets questions from this. They can ask you the rate or ask you concentration. So if you don't know it properly, you are going to pick the wrong answer, definitely. The next we have here is temperature, pressure, and concentration affects equilibrium. Equilibrium for enclosed system. Closed system, that's where equilibrium functions. Only what affects equilibrium there is the temperature, pressure, and concentration. These 3 determinants affect equilibrium. So the fifth one we have here is equilibrium can be dynamic, which means reactions still occur in both directions. So when you say it's dynamic, so the product and the reactants are replaced concurrently. That's a dynamic reaction. So these 5 characteristics are those of the chemical equilibrium. Types of chemical equilibrium. We have 2 types of chemical equilibrium for this level. The first type we have here is the homogeneous equilibrium. What does the homogeneous equilibrium mean? When you hear homo, it means one. Homosexual, one kind of sexual partner having sex together. Homo. When you hear hetero, it means different origin. This one might come from this side, this one from another side. They are not one. They are not one kind. Two different kind coming together. But when you hear homo, same kind coming together. So the first one we have here is homogeneous. When you hear genius, just know that you are talking about generation, evolution, how something came about, establishment, okay? How something came about. That's genius. When you hear genius, generation, generates, okay? So when you say homogeneous, same generation, same origin, that is homogeneous. So homogeneous equilibrium here is, it says all reactants / products are in the same phase. Can you hear it? The same phase. Can you hear it? The same phase. So for example, 1 mole of nitrogen gas here and 3 moles of hydrogen gas molecule here gives you what? 2 mole of ammonia gas. That's it. Forward and backward reaction equal. The concentration are constant but not what? Equal. So the next we have here is the heterogeneous equilibrium. And what is the heterogeneous equilibrium? Reactants and products are in different phases. Reactants and products are in different what? Phases. For example, you can see this limestone we have here reacting reversibly. This one is dissociation. Okay, you are breaking this to give this, and this can also combine to in turn form the reactant again too. So different phases. So when you say homogeneous, same phase. When you say heterogeneous, different phases. How do you know if the compounds or the reactant and the product is in same phase or different phases? Let me tell you. Just look at the reactant and the product. Are they in the same states of matter? Are they in the same states of matter? Like this one, we have homogeneous, one phase. We have gas here. We have gas here. We have the products also gas. When you look at the heterogeneous, more than one phases, we have solid here. On the reactants, we have gas here. We also have solid here on the reactants, and we also have gas here. So you can see this one is mixed. This one is not gas, 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 or solid, 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 true, but this one is gas, gas, gas. So this one phase, that's one state of matter, gas, 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 that's homo. Then for the hetero, more than one phase or more than one state of matter. In the enter, ensure you are jotting down. The first one here is units depend on the reaction. Sometimes none, okay? Sometimes none, but units depends on the reaction. The second one is pure solids and liquids are not included in equilibrium constants. Pure solids and liquids are not included in equilibrium constant. That's the concentration are not constant. Pure solids and liquids, but is highly constant in gaseous reactants and products. The third we have here is a large equilibrium constant, which is an equilibrium constant greater than 1. Okay, you know the greater than, lesser than, greater than, lesser than. Greater than 1 equals reaction favors product. So when the equilibrium constant is greater than 1, you can see this in your JAMB UTME. Just know that the reaction is going to favor the product. Okay, it's going to favor the product because the equilibrium constant, the concentration of the reactant is greater than the product. So the reaction is going to favor the forward reaction. So when you understand this equilibrium very well, you don't even really need to be cramming all this. Because I've explained everything. So when you say the equilibrium constant is greater than 1, it means that the concentration of the reactant is greater than the concentration of the product. So more products are going to be formed because the concentration on the reactant side is higher than what you have there in the product. So is the reversible reaction, that's the reaction on the right hand side, is going to be impeded because of lower concentration of products. And the fourth we have here is a small, that's in turn, a small Kc, that's equilibrium constant, is less, that's an equilibrium constant less than 1. Okay. Reaction favors reactants. It means that more reactants are going to be formed. So it's going to favor the backward reaction or the reversible reaction to favor the formation of more reactants. So that tells you that the concentration of the product is higher than the concentration of the reactant. Then the fifth one we have here is factors affecting equilibrium is the Chatelier principle. And we are going to treat that now. Chatelier principle states, this man I told you about, this chemist, this great chemist, the father of equilibrium. His principle states when a system at equilibrium is disturbed, so a system that was at equilibrium, you go there and you disturb it. It shifts to oppose the change. When you disturb it, it's going to adjust. It's just like a human being. You give me slap. You give me slap. As you give me slap, I am going to adjust to bear the pain from that slap. I am going to adjust. I'm going to do like this. I'm rubbing my cheek to help me abate the pain, and simultaneously I'm still using my hand to protect my face from a further slap or a subsequent slap that might come after you slap me that first one. So those are adjustments, okay? Those are shifting, coping mechanism. That's the same way that an equilibrium, a system in equilibrium is going to shift, cope, adjust when you disturb it. What can disturb a system at equilibrium? Wetin fit disturb this system with the equilibrium? we only have only three determinants. You know, we have up to 6 determinants of a chemical reaction or a chemical process. Okay, for a chemical process to occur, you have up to 6 determinants. Okay, but for equilibrium, remember, an equilibrium occurs in an enclosed environment. Okay, an enclosed system. So you only have 3 that affect equilibrium, which is concentration, pressure, and temperature. 3 of them. Let's treat each of the 3 one after the other. Effect of concentration. JAMB like this one well. The 3 of them. Effect of concentration. Get your pen and paper. The first one we have here is increased reactants. When you increase reactants, it shifts forward. Okay, so the forward reaction is favored when you increase the reactants. Like we explained before when we were explaining equilibrium constant, where equilibrium constant is greater than 0, it's going to favor the forward reaction. That's the same thing you are seeing here. So when the equilibrium constant is greater than 1, it shows that the reactant has been increased. Greater, increased reactants. Lesser than 1, increased products, lesser reactants. So greater than 1, greater reactants. Lesser than 1, lesser reactants. So you now understand what is going to occur. When you increase the product, the equilibrium shifts from right to left. So it shifts backward. So the backward reaction is going to be favored. So more of the reactants are going to form. So the thing shifts from this right hand side to the left hand side. So the reversible reaction is favored. When you remove products from the system, that's we are talking about effect of concentration, because when you are increasing reactants, you are altering the concentration. You reduce reactants, you are altering the concentration. You remove products, you are altering the concentration. When you remove products, the equilibrium shifts forward. So when you remove products, there are no more products on the right hand side of the reaction to manufacture or to produce the reactants. So when you remove products, the backward reaction is not going to be favored. So more of the forward reaction is going to occur from the reactants, because the reactants has an adequate amount of reactants or compounds or elements depending on what is undergoing the chemical reaction. So since the reactant is piling up, reactants are piling up, it's going to favor the forward reaction. More products are going to be formed. Forward reaction is going to be favored when you remove the products. So that's that for concentration. Then the effect of temperature. Okay, take note of the color coding. This is red, very hot. Something is hot, red hot. The first effect of temperature we have here is if reaction is exothermic, that's heat is evolved during the chemical reaction. Heat is a product. Okay, if the reaction is exothermic, that's heat is evolved. So heat is a product. Heat is part of the product of the reaction. The second one we have here is when the temperature is increased. Okay, you increase the temperature of the system, the equilibrium shifts backward. That's the reversible reaction is favored. More reactants are formed. Okay, more reactants are formed. More products combine to form reactants. Okay, so the equilibrium moves to this side, to the left. Then the third one here says, so what will happen when you decrease the temperature? It's going to shift forward. That's the opposite of increasing of temperature. Okay, instead of shifting backward for increased temperature, decreased temperature makes it shift forward. So more reactants are going to combine to form products. Okay, so the fourth one here is if reaction is endothermic, heat is a reactant. So if reaction is endothermic, heat is a reactant. So you all know that endothermic is here, exothermic is here. Endothermic is on the side of the reactant, while exothermic is on the side of the product. So the fifth we have here is increased temperature shifts forward reaction, and decreased temperature, okay, backward reaction. The same thing we explained here. So in this effect of temperature you are seeing here, it was classified into 2. This is for an exothermic reaction. Okay, for an exothermic reaction, these 2, increase in temperature will shift the equilibrium backward. That's if we favor the backward reaction. But decreased temperature will favor the what? The forward reaction. It's simple because this is exothermic reaction. Heat is given out. So when you increase the temperature, because this reaction does not need heat to occur, that's why heat is given out. Okay, the heat of the reactant is already enough. So when you increase the temperature, it's going to favor the backward reaction. Okay, because this reaction does not need heat. It's an exothermic reaction. But when you decrease the temperature, it's going to favor the forward reaction, because this reaction does not need a high temperature to occur, because the heat of the reactant is already enough for the reaction to occur. But when you look at this other side, if the reaction is endothermic, that's heat is a reactant. Okay, heat is the reactant. So heat is part of the reactant. Heat is part of what is required to make this reaction occur. So when you increase the temperature of the system, it's going to favor the forward reaction. The equilibrium shifts to the right. Forward reaction is favored. But when you reduce the temperature, you know that temperature is one of the requirements for an endothermic reaction to occur. When you reduce the temperature, it's going to favor the backward reaction, because reactants can't combine to form products again, because it needs a high temperature to occur. Let's look at the effect of pressure. The first effect of pressure here is increasing pressure shifts equilibrium to the side with fewer molecules of gas. So just know that the effect of pressure only works for gas. It's only applicable in gases, okay? It only applies to gases. Only gases for pressure. So the first we have here is increased pressure shifts the equilibrium to the side with fewer molecule of gases. You are only concerned with the molecule of the gases. That's what you are looking out for when you are looking at pressure, okay? When you are trying to detect the effect of pressure in the system, you are looking at the molecules of gases. The part of the reaction or the part of the equation where the mole of the gases are high, just know that such part is not going to be favored, okay? The equilibrium will not shift to that part. The equilibrium shifts to the part with lower molecules of gases. Let's read it again. Increased pressure shifts the equilibrium to the side with fewer molecules of gas. So when you increase the pressure of the system, the equilibrium shifts to the part of the reaction or to the side with fewer molecules of gas, either on the reactant side or the product side, depending on where the molecules of the gases are fewer. So you have to figure that out when you look at the chemical equation. Let's look at the second one we have here. The second one is decreasing the pressure now in turn shifts to the side with more molecule of gas. So when you now reduce the pressure of the system, the equilibrium shifts to the part of the reaction with the higher molecules of gas. You understand? It could be on the reactant side or the product side. That's why you have to look at the equation to know the part with higher or lower molecule of gas. So increased pressure shifts the equilibrium to the part of the reaction or the side with the lower molecule of gases. But decreased pressure favors the part or the side of the reaction or shifts the equilibrium to the side of the reaction where you have the higher molecules of gases. Then the final one, there is no effect if the molecule of gas are equal on the sides. So when the molecules of gases on the left hand side of the reaction equals that on the right hand side of the reaction, there is no effect when you increase or decrease the pressure. Pressure is not going to have any effect in the system. If you like, increase the pressure, nothing is going to happen. Equal when the molecule of gases on the left side and on the right side are both equal. So let's look at the effect of catalyst. A catalyst speeds up both forward and backward reaction equally. That's the effect of catalyst in a system at equilibrium. Catalyst does not change the equilibrium constant or equilibrium position. Catalyst does its thing equally. So when you introduce a catalyst into the system, it favors the forward reaction and the backward reaction equally. It favors the left hand side of the reaction and the right hand side of the reaction equally. It favors the reactants, the combination of the reactants and the combination of the product equally. So catalyst runs an equal role both on the left hand side of the reaction and on the right hand side of the reaction in a system at equilibrium. Let's look at the uses of equilibrium, which is JAMB's favorite. Industrial use, like I said before, is JAMB favorite. First we have here is the Haber process, which is the commercial manufacture of ammonia or industrial manufacture of ammonia, whereby 2 molecules of nitrogen gas reacts with 3 molecules of hydrogen gas reversibly to give 2 molecules of ammonia gas. The reaction is an exothermic reaction because heat is evolved. That's why you are seeing heat here. Heat is evolved, okay? Heat is evolved during the reaction. And when we apply what we have learned under temperature, when you reduce the temperature of the system, low temperature is going to favor the forward reaction because an exothermic reaction does not need heat to occur, okay? The heat of the reactant is already enough for the reaction to occur. So the heat of the reactant is higher than the heat of the product. So the second we have here is high pressure favors forward reaction. Remember, pressure is only applicable to reactions involving gas, and this is one of them. Okay, so ammonia is a gas, nitrogen is a gas, hydrogen is a gas. So high pressure favors forward reaction. Why does it favor forward reaction? Remember the law of pressure. When you increase the pressure of the system, the equilibrium shifts to the direction of the reaction where you have fewer molecules of gases, and the right hand side of the reaction has the fewer molecule of gases, which is 2 moles of ammonia gas. When we look at the left hand side of the reaction, we have 1 mole of nitrogen here and we have 3 moles of hydrogen here. And you look at the right hand side of the reaction or the backward reaction, you have 2 moles of ammonia, okay? And remember the law, when you increase the pressure in a system at equilibrium containing gases, what is going to happen is going to favor the part or the position of the reaction where you have the fewer molecules of gases. What part of this reaction or this equation has the fewer molecule of gases here? That's the backward reaction on the right hand side of the reaction, having just 2 molecules, okay? So that's that for that. When you increase the pressure, it's going to favor the forward reaction, okay? More of this is going to combine to form more of ammonia. So when you look at the statement in the bracket, it reads fewer moles of gases, 4 on the left hand side, then 2 on the right hand side. The catalyst used is iron, okay? Iron, sometimes potassium oxide and aluminum oxide might be used as adjuncts. So the next industrial process we are looking at to further illustrate what we have learned so far is the contact process, which is the production or the commercial manufacture of sulfuric acid or the industrial manufacture of sulfuric acid, where 2 moles of sulfur 4 oxide is reacted with 1 mole of oxygen reversibly to form 2 mole of sulfur 6 oxide. So favored by moderate temperature. Okay, so this reaction is favored by moderate temperature. Remember, when you increase the temperature in a system that is endothermic, an endothermic reaction. Okay, when you increase the temperature, it favors the forward reaction. So this system is endothermic. You increase the temperature, it favors the forward reaction. And when you increase the pressure, you know what's going to happen. On the left-hand side of this reaction, we have just 3 moles of gases. One on the right-hand side, we have 2 more. When you increase the pressure, it's going to favor the forward reaction. That's why they say the reaction is favored by moderate temperature and high pressure. So the catalyst uses vanadium 5 oxide. All right. The third industrial process we are going to look at here is the production of methanol. This is the chemical formula. Just 1 mole of carbon 2 oxide reacts with 2 moles of hydrogen gas to give us methanol. Gas we have here is, we have 3 moles of gases here, and when you increase the pressure of this system here, it's going to favor, pressure is going to favor this reaction. Okay, high pressure is going to favor this reaction. Let's look at some key points to memorize for JAMB UTME concerning this topic, equilibrium. JAMB key points to memorize. The first one is equilibrium is dynamic, not static. So equilibrium, the equilibrium of a chemical reaction or chemical equilibrium in an enclosed system is dynamic. It changes. It's not static. It's not in one place. Not like some equilibrium in physics. Okay, like the beam balance. That thing you see in the law court like this. You put weight here. You put equal weight here. There is a static equilibrium. You achieve a static equilibrium. They are equal and they maintain an equal position, or such as the seesaw. Okay, the seesaw. If the 2 persons on a seesaw are having equal weight, that's a static equilibrium. There's a balance in both levels of the 2 ends of the seesaw. So that's a static equilibrium. But for chemical equilibrium, it is dynamic. It changes, it moves. For this to be balanced, this has to occur. More of this has to react for this to occur, and so on and so forth. So Kc, which stands for the equilibrium constant, only changes with temperature. That's a fact. It only changes with temperature. Higher temperature, okay, when it's greater, when Kc is greater, it favors forward reaction. When Kc is lesser, it favors the backward reaction, like we discussed. Catalyst does not shift equilibrium. It favors both sides equally. Okay, it favors both the forward reaction and the backward reaction equally. So solid/liquid do not appear in equilibrium constant expression. Okay, so equilibrium constant is only applicable for gases. Do not forget that, only for gases, please. That's why I'm saying always make your notes. Okay, so increased pressure favors the side with fewer gas molecules. Okay, increased pressure favors the side of the reaction with fewer gas molecules. So remove products, reaction or equilibrium shifts forward. Forward reaction is favored. Okay, so when you remove products, because there's no products to form a reactant again. Okay, so the same thing, when you remove reactants, more products is going to favor backward reaction. More products are going to combine to form reactants. Okay, so when you add heat to exothermic system, what is going to happen? Backward reaction. Okay, the equilibrium is going to shift backward, because you know that an exothermic system does not require heat to establish the reaction. So it doesn't require heat to establish the reaction. So heat is not good for exothermic reaction. You don't need heat, because heat is going to be evolved. So instead of it to favor the forward reaction that is exothermic, it's going to favor backward reaction. That's like the dissociation of what you have there to form the reactants, or dissociation of the product to form reactants, usually achieved by heating. Now that we have understood everything, let's go back to the JAMB must repeat question. Remember the question, JAMB must repeat question 3. The question reads, in the equation above, the effect of increased pressure on the equilibrium position is that, according to what we have learned, the last option here, option D, more hydrogen gas is formed or produced. That's wrong. Why is it wrong? When you look at this system here, we have solid here. Okay, we have solid here, copper oxide, solid, and we have gas here. Okay, hydrogen gas. And when you look at the right hand side of the reaction, we have copper, solid, and we also have steam, which is gaseous. Okay, and we were taught that pressure only operates on gases. Okay, and we have gases in the reaction, and we have gases on both sides of the reaction. We have both on the left hand side of the reaction, and we have gases on the right hand side of the reaction. But one thing that we always look out for is the mole of the gases when we are dealing with pressure. So it's the mole of gases that you are going to use to determine if pressure is going to increase pressure or decrease pressure, the effect that increased pressure or decreased pressure is going to have on the system. Okay, so the mole of gas we have here is 1 mole of hydrogen. On the right hand side of the reaction, we have 1 mole of steam or water. Okay, so we are going to look at the options at the top. So we now know that we have equal moles of gases on both sides. We already know the answer. So the smart ones already know the answer. So A, or if you have taken this lecture, you should know the answer. So A, the equilibrium is shifted to the left is wrong. B, the equilibrium is shifted to the right is also wrong. Or for your correct option, option C, there is no effect. When the mole of gases on the left side of the reaction and the right hand side of the reaction are equal, there is no effect of increase or decrease pressure on the system at equilibrium. But when you increase pressure, it favors the side with the smaller mole of gases. When you reduce pressure, it favors the part of the reaction or the side of the reaction with the higher moles of gases. Thank you so much for taking this lecture. I hope you enjoyed the lecture and you made your notes for subsequent revision. Do not forget to follow across all social media platforms at Nkwado Augustine. I will see you in the next class. Congratulations on earning your free mark in JAMB UTME 2026. If I have added value to your life through this lecture, help me hit the like button and appreciate me in the comment section. UTME candidate 2026. No lose that free marks. Oh. Peace. Peace out. I'm out.